in the audience today, if you raise your hands, have been involved with ATSC 3 at all so far? Okay. Anyone?
Okay, we're all going to learn something. There'll be a test afterwards.
Yes, there will be a test afterwards. Okay, so I just wanted to know how to talk. I've been giving ATSC 3 presentations now for about 5 years, so I want to know who I'm talking to. Before I go into the presentation, I will do the mandatory advertising for the company. I'll explain who we are. We're the Elenos Group. Most of you have probably heard of Broadcast Electronics, BE, but not of the Elenos Group itself. So we're made up of 4 companies. Elenos in Ferrara, Italy. That's the northwest side. Itelco focusing on Elenos focus on small low-power TV radio transmitters. Itelco focuses on a whole range of television. Broadcast Electronics, all TV, radio, AM and FM. And the last one, a company called Pro Television from Copenhagen in Denmark, and they focus on digital modulators. Okay, the normal crowd I present to actually have listened to 1,000 ATSC 3 presentations. So this is just a real quick, what the heck is ATSC 3 and why we're doing it. So if you can read the headlines here, it's configurable, scalable, interoperable, and adaptable. So what the heck does that mean? Basically, it means that we're talking today, we have ATSC 1, and we decided to move to ATSC 3. The first question is, what happened to ATSC 2? So it failed miserably because it was designed to be backward compatible, designed with a lot of inability to actually move to the next generation. So it was designed, but they moved straight from 1 to 3. It's configurable. It means it can be adjusted and adapted to your scenario. It can be adjusted to what you need to do, whether your customers are the ones with a cell phone, with a big screen TV, a laptop. It's designed for you to target that person or many different people. You can do 2 or 3 at the same time. It's scalable. You can start off just focusing on one group of people. You can focus on different types of markets, and you can keep expanding the number of channels, the number of content, or different types of content. It's interoperable. It basically uses an IP standard, which means it talks to computers. And computers now, you can actually start to talk about apps and all kinds of interactive program. And it's adaptable. And already they're thinking about ATSC 3.1. So it can be upgraded. It's always going to be designed to be fully backward compatible, unlike ATSC 1, which was really designed for one standard and one standard alone. It provides, obviously, HD, immersive audio. As I said, it uses IP. One of the key things, though, it does actually have a standard of OFDM. ATSC is the only standard in the world for television, for radio, for communications that uses a single carrier system instead of an OFDM system. In my opinion, it was a terrible choice, but that was 20 years ago. We have emergency alerting and, as I said, interactive applications. If you do actually have any questions, I guess you can ask at any time. Feel free to raise your hand. Okay, I'm going to start talking, and there's going to be a lot of acronyms. So many acronyms, I cannot remember them all. So if you do actually have a question about one, I may actually have to look it up. So this is the actual broadcast chain, what you have with a ATSC 3 system. It's not too different to an ATSC 1 system. You have an encoding system, you have a multiplexer in a sense. The middle item here, the scheduler or gateway, that's the new item. That's something that you don't have in ATSC 1. And then, of course, a modulator and a transmitter system. We can split it up into two parts. Usually the encoder and the broadcast stream generator is located at the studio. The scheduler, the gateway in the middle, can be either at the studio or at the transmitter site, depending on whether you want to do multiple frequency networks or single frequency networks. The middle section, that's where it all happens. That's where ATSC3, it's called the bit interleaving coding and modulation chain. And that's the center section, and that's what I'm going to talk about a little bit today. And jump in and talk about that. So I'll just jump through that. This is the actual chain of the actual inside the modulation and coding section of the system. I'm going to have to stand here and read it out. So the first item is an LDM. It's layer division multiplex. That's like hierarchical modulation in DVB-T that's used in Europe. It's basically sending out signals on the same level, the same frequency, but at actually a different level, usually 3 or 5 dBs down. Hierarchical modulation can be used so that you can send on the higher level a very high quality signal, and on the second level a lower quality signal but a much more robust signal. Hierarchical modulation never really caught on in Europe, so I'm not sure it will catch on here, but it's the first thing in the chain that you actually have to make. Then you do then you do time interleaving, then you do an OFDM framer frequency, because you've changed the signal from a time domain to a frequency domain. Then you do a scattered pilot inserter. That means you're putting pilots in the system so that you can do timing and measurements on the actual OFDM channel. Then you finally actually do turn it into an OFDM signal. You then put it through a peak to average power ratio reduction system that helps the efficiency of the transmitter itself. You put in some guard interval. And then finally, what's called the bootstrap insertion. That the bootstrap is the first part of the signal, the last part of the insertion here, but the first part of the signal that tells the TV receiver what it's getting, what kind of information it needs. LDM, as I said, it's basically, you can send 2 signals. The system ATSC3 actually is designed to have as many as 3 signals in one band. And as I said, you can send a high quality but less robust signal as the main one. In the middle, you could do a much more lower quality but much more higher robustness, and there's even the option to do a third level. The encoding is not new. It's a standard that's HEVC, high efficiency video coding. It's been around quite some time. It's a fairly standard in the industry. One of the key issues here is that it is 4 times that more efficient than our current ATSC1 standard. So straight off the bat, you've got 4 times the quality or 4 times the content of ATSC1 without doing anything at all. Output is MPEG-. MPEG- stands for Dynamic Adaptive Streaming over HTTP. Again, HTTP being web browsing and interactive on computing. You can do standard definition, high definition, and ultra high definition as a standard video encoding system. So the next product, the next item in the chain after the encoder is what's called the broadcast stream generator. This is like a multiplexer in ATSC1, where today a multiplexer just combines different video signals, video channel 1, video channel 2, and so forth. But this is a slightly different one because it can actually multiplex different types of content. Not just video, but the electronic signal guide, service guide. It can also do applications, multiple direction applications. It can also, which can be used for nonlinear and linear and non-real-time content. For instance, you could be at night, maybe send data over this system. It could be recorded on a home hard drive, and You could record 1,000 movies overnight and then use that as a pay-per-view kind of content. The Advanced Emergency Alert System, and, of course, a security file generator. That's a system to protect your content, your rights. The input, as I said, is MPEG-. The output is route MMT. And we move to the next item, the scheduler. And as we move along, it gets more and more complicated. So just thought I'd throw that out. The scheduler is new in the system. It can be located at the transmitter site, actually inside the exciter, or it could be on the server or in the cloud. The scheduler's main job is to actually generate the preamble, which is the bootstrap and the preamble. It's basically the information to tell the receiver, the TV, what's coming next. The channel, all the data that's required to make the receiver work. Also, it has the emergency alert wake-up bit, which means if you have a particular type of radio or TV, it will actually wake that TV up in the middle of the night to tell you there's an earthquake or there's something coming that's bad. So the waveform here is made up of first the bootstrap. The second part is called layer 1, L1 basic, and the third part is L1 detailed. And it gets more and more information as we move through the stream to again tell the TV receiver what's coming next. There's not much setup to do in this part of the bootstrap and L1 and L2, but of course there is a lot of setup to do in the payload, and I'll get into that later. So here's your house. I'm now going to explain what a physical layer pipe is, and it's sometimes called physical layer pipe or physical layer protocol. So today you have one signal. It transmits in one direction, one way, to one type of antenna. It was designed to be received at about 11 meters off the ground. It was designed to be received with an outdoor antenna. ATSC 3 is totally different, and that's where the big change is. It's adjustable. It has many handles to make adjustments on what type of information is being sent, whether it's ultra-high definition, standard definition, whether it's for mobile, or whether it's for non-real time. So with the first PLP, and this is just an example, the first PLP could be obviously designed just to replace ATSC 1. You're going to target a signal straight to the rooftop, standard definition, high definition, not a big choice there. For the second one, you could actually put a second signal on the same transmission and transmit PLP2, and that would be aimed at maybe a lower quality, but a much more robust signal. A signal that goes inside the house, goes through one or maybe two walls. A third PLP could be designed and transmitted at the same time, of course, that's aimed towards a smart device, a mobile device, a phone, radio, some kind of portable device. And then the fourth, we could actually do a fourth PLP, which is aimed at potentially non-real time, and that could be a hard drive inside a set-top box, where during the day you're just downloading, and again, this is just an example, Netflix movies. Tens of thousands of data of movies, and then people can select them and buy them just like they're on Netflix. But this is one to many, and so the cost per bit is incredibly more efficient than one-to-one. Okay, so how does it work? I'm actually jumping to the actual setup of how you would make, and this is something I probably would like to explain most of all, is that ATSC 1, there is no adjustments. You switch it on, get the encoding, get the transmission looking good, and that's it. ATSC 3, there are a lot of adjustments. The first decision as a broadcaster you're going to have to make is, who is my customer? What kind of receiver will they have? Will they be maybe inside a car, watching this on a phone? That way you would actually have to do something like a low capacity but very robust signal. Or is it somebody who's watching a huge TV in their living room and they have an antenna on the roof, and that would be a high capacity but less robust signal. And of course, in the middle is where we are today. ATSC 1 is just below the actual maximum capacity line. So the decision as a broadcaster, who's my customer and what kind of signal do I need to transmit? So the adjustments, and I just did a quick calculation here. I did this on the way here today. There are 46 modulation and coding combinations. There are 3 types of fast Fourier transfer methods. You then have 7 guard intervals, and then you have 12 pilot choices and 4 pilot patterns. So the adjustments that you can make are 74,592. So that's going to take you a while just to get all of those organized. So the question is, how the heck do you do that? Because that's 74,000 things you can do wrong. Almost. So first of all, I'm just going to scan through these fairly quickly because I think we're a little way before we'll be implementing it. But you're going to choose, are you a single frequency network or a multiple frequency network? Is the scheduler, the gateway, is that at the transmitter site, or is it at the studio? Am I in Korea or in North America? That one's a fairly easy one. So. The first item is the bootstrap. As I mentioned, this is a fixed set of data. The data is organized, again, very basic information to literally wake up your receiver to tell you, I'm getting channel 26, it has 4 programs, it's OFDM modulation, it's et cetera, et cetera. So that just gets the TV going. Then you have L1 basic. Again, there's not many adjustments in here. You don't really have to do that much work. You do have to choose the actual pilot quantity. There are a different number of pilots. The more pilots you have, the more robust the signal is, but of course, the lower the payload. And that's the rule of ATSC 3. The more robust you make the signal, the less the payload. You have to choose FEC types and the peak to average power ratio options as well. Then we look at L1 detail. Now it's getting a little bit more complicated. You have to choose the FFT and the guard interval. And you have to, again, choose the number of selected, to select the number of scattered pilot patterns. And there's more. And it keeps going on and on and on. Now we actually, we choose the code rate, we choose the CTI depth, that's the interleaving depth, we choose the FEC, and we also choose the forward error correction. And it just keeps going on and on. We have the cyclic redundancy check, the type of modulation, and that's a really key one, because that really does determine who your customers are. Hybrid time interleaver, which type of interleaving, and of course, whether you're actually going to do LDM multiplexing. And in practice, it's just 5 easy steps, he says. This is a web browser from one of our modulators. This is at the top here, is basically a schematic of the actual transmission, and then these are just drag and drop boxes to look inside each one. If you click on the frame view, you get this. This is the actual scheduler setup, and this is where you would set the bootstrap, which is this one here, L1, and this is your actual payload here. So you literally grab hold of this and drag them down into various places, and then you can actually set all of those adjustments that I mentioned before. So step 1 is select MFN, SFN, and so forth. Step 2, step 3, make all of those selections, and then the good news is there is a parameter validator. And that means it tells you if you cannot do what you're trying to do. It basically says, wow, you've set the SP pattern is invalid. It should be either 12/2, 12/4, and so forth. So it gives you a clue of where you've gone wrong. Now, it doesn't mean that you've got the perfect signal just because you've got no invalid notification. You could be still sending out a really bad signal, or a signal that's not going to be received by your customers. So I'm going to jump through this. You just drag and drop each one of those, you make the selections, and you move forward. To step 5, this is where you would set the payload and more. So how do you actually go about doing this? How do you actually start? I mean, where do you start? And so the key is you basically set some standard settings, whether you're aiming for a high bit rate, but low robustness, or the other way around, or somewhere in the middle. And there are standard settings that you can start off, and then you actually then have to experiment in terms of receivers, in terms of the customers you're getting. Are they really getting the best signal? You can start to increase the bandwidth and reduce robustness, or you can decrease the bandwidth and increase robustness as the customers need. So you can start here. This is an example for a very high payload, but low robustness. The FFT would be 32K. That means you've got 32,000 carriers, a pilot pattern of 24/2, a guard interval. So 24/2 means you're replacing only 2 of the 24 signals, repeating them. So it's a fairly low repetition rate. You're choosing 256 QAM and a code rate of 9/15. And you would get a signal here, which is around 28 megabits per second, which you then could put any kind of signal you want that's broken up into 28 megabits. So that would be a high capacity, very low robustness. You could choose the middle. Again, we've kept the 256 QAM, but we've started to change some of the guard interval and the code rate. So this is somewhat similar to ATSC. It's going to be around 18 megabits, 19 megabits per second. But of course, don't forget, you've got 4 times the actual capability due to the type of encoding. We're done on time. Good. And then there's the third section, which would be much lower bit rate, but a much more robust signal. And this signal would be in the signal-to-noise ratio of about 8 dBs. So, as an example, ATSC1 is 15 dBs. You need at least 15 dBs signal-to-noise ratio to receive an ATSC1 signal. This would be more than twice the noise level and still be received by a standard receiver. And that's basically it. You would choose that and then make slight modifications on all of these settings, slowly moving up the graph or down the graph, depending on who your customers are. That's the actual end of the show, I think. Thank you very much.